Okay, so let me start today. So how are you? So this is the third week of this course. This is SeungryongKim. Okay, so let's start. So today we are going to talk about the logistic regression problem. So actually today's lecture is related to the classification problem. So in the last week, we talked about the regression or the linear regression problem. So before starting, let's recap what we've done so far. Okay, so it was the last week. Okay, so the last week, we talked about the relationship between the regression problem and classification problem in computer vision application. So, for example, as you can see here, in some application, we would like to estimate the depth information defined in the continuous space, or want to segment some object or the scene defined in the categorical space. So this is called the depth estimation problem or the semantic segmentation problem. So first of all, in the last week, we've talked about this regression problem, and today we will talk about the classification problem. Okay, so it was the examples of the regression, right? And what's the regression? The goal of the regression is to either predict the output of the new input or to understand the effect of input on the output space, right? So yeah, so to define the regression problem, we need a data set consisting of the input xn, right, and the output yn. So in the regression problem, yn should be the continuous value, for example, like a real value. There were two goals of the regression problem. First one is the prediction, and second is the interpretation, right? To define the regression problem, first of all, we have to define the linear mapping function. For example, something like this one or this one, right? This linear mapping function represents the straight line. So, and it consists of the only linear term, not a non-linear term, right? Like this one. And first of all, if you think about the very simple case, so if there is a one input feature vector xn and one output feature vector yn, we'd like to find out the W0 and W1, right? So if you have the W0 and W1, we can define the mapping function, something like this, right? And how can I find this parameter W? So to estimate the parameter, we need to define the cost function first, right? Then what is the cost function? Cost function is the distance between the ground truth y and the estimated fwx, right? So here's things. So the cost function is the distance here, and the loss function is the aggregated of the cost function. But we can use we can also call this LW as a cost function. So there is no definite exact terminology, but so we can use the cost function or the loss function or the energy function, something like that, simultaneously. And our goal is to estimate the W that minimizes this cost function, right? So this is the optimization. And right here, so cost function quantify how well our model explains the data, or in other words, how costly our mistakes are, right? So for example, how well our model explains the data means the cost is defined function of the fwxn with the yn, right? And how costly our mistake means our mistake defined as the difference between estimated output with the ground truth output. Let's say this is error, right? So cost function represents something like that. And yeah, here was some intuitions of the cost function, right? So in the last week, we drew some cost curve defined here, right? So first of all, the cost function should be symmetric, right? And in the two-dimensional, in the two-parameter case, we can draw the cost curve, cost surface, like this one. Our goal is to estimate the minimum value among this cost contour. And yeah, there was two very well-known cost examples. The first one is the MSE, mean square error. Second one is the mean absolute error, called the MSE or MAE, right? So if we define the error between the the estimated values and the ground truth yn, then we can draw this cost curve with respect to the en error of the n sample, right? So MSE of the MSE in terms of this error will be looks like this, or if MAE represent this kind of the function, right? So there were two kinds of desirable property of the cost function. The first one is the symmetry. The second one is the large mistake, and very large mistake should be dealt with equally or similarly, right? So we talked about the robustness for the outlier. Here was the further cost function, something like this one. This cost function is called the robust cost function. What else? Okay, so if you define the cost function, we want to find out the parameter W that minimizes this cost function. The first thing we can do is to use the grid search algorithm. So in grid search algorithm, we can compute the cost over the whole value W in a grid and pick the best, right? So this is very brute force, but extremely simple. But it has too many for loop, resulting in exponential computational complexity. So we need a more systematic way to solve this problem. That's why we introduced the gradient descent algorithm, right? What was the gradient descent algorithm? Here's the thing. So gradient was the slope of the tangent to the function. So as you can see here, let's say we have a function, something like this one, right? Let's say we are here, right? Then the gradient means of the slope of the tangent function. In this case, this function, right? Then the slope of this function, the slope of this function means the gradient, right? At this point, and the gradient descent means we have to move the negative direction of the gradient, right? So this was the gradient descent, the strategy of the gradient descent algorithm, right? So yeah, it was the outline. Yeah, there are three kinds of terms in gradient descent algorithm. So first one is the initialization. The second one is the direction. A third one is the step size, right? And here are things. Okay, so this represents the one step of the gradient descent algorithm. So each step we have to update our learnable parameter W0 and W1 using the partial gradient in terms of the W0 and W1, right? And to compute the gradient, there is two kinds of way. The first one is the numerical gradient. Second is the analytic gradient. We've talked about this one. To summarize, we formally use the analytic gradient because this is much accurate. This is more accurate than the numerical gradient, and this is much faster than previous numerical gradient one, right? What else? There were property of the gradient descent algorithm, right? So, and yeah, we also talked about the learning rate, right? So in this phase, we summarize. We found that the proper learning rate is one of the most important issues in the gradient descent. And what else? It was the limitations of the gradient descent algorithm. It is easy to get trapped on the local minimum. And yeah, and we also extend this single feature case into the multiple feature case, right? So in here we define the much higher, much complex mapping function. Define something like this one, and for sake of the notation, we from now on we define this linear regression mapping function as a WT transpose XN, right? So this is called the dot product of the W and XN. So this linear regression problem is also called multivariate linear regression problem, right? And yeah, then we can reformulate the gradient descent for the multivariable case, something like this. Okay, so yeah, it was the last week. Okay, let's move to the today's lecture. Okay, so today we're going to talk about the logistic regression problem or the classification problem. Yeah. So here's the thing. So similar to the regression problem in the last week, the classification problem relate the input variable x to the output variable y, but y can only take on discrete value comparing to the regression problem. For example, y can be one of the term in the discrete space, something like 1, 2, 3, number of things. So this is the discrete values, right? This discrete value is also called the categorical variable. Right? So the main difference between the regression problem and the classification problem is the type of the output data, right? So here's an example. For example, if we want to classify the email as a spam or the non-spam, we can say that the output will be output is 0 or 1, right? Another example is here. In online transactions, we would like to classify the one online transaction as a fraudulent or not. So in this case, fraudulent is going to be y is equal to 0, maybe y is equal to 1, or the non-fraudulent is meaning the y is equal to 0, right? Another example is tumor classification, right? So based on some features from the tumor data set, we can decide this tumor is malignant or the benign. So it might be y is equal to 0 or y is equal to 0. So, or we can use the inverse notation. For example, y is equal to 0 or y is equal to 1. It doesn't matter. Anyway, in classification problem, we can define our output variable in the categorical space. For example, 0 or 1. For example, in this case, 0 means the negative class. For example, the benign tumor, or the y is equal to 1, which means the positive class. For example, the malignant tumor, right? This is examples of the classification problem. Okay, then how can we do that? How can we solve the classification problem? Here is the example. So let's think about the tumor classification problem. Let's say we have a training data set consisting of the tumor side. Let's say this is the input data, and the malignant or not. Let's say this is the yn, And here is a training data set, something like this one. For example, this is the x1, y1, and this is x4, y4, like this, right? For example, x1 might be 0.21, y1 0. In this case, x4 is equal to 10, or y4 is going to be 1. In this case, how can I find the model that explains this data set well? How can I find the model that will approximate this data set well? First thing we can do is to use the linear regression, that is define the straight line, right? Okay, so let's think about the regression problem first. Regression technique first. So if we find out the linear mapping function using the regression problem, it should be something like this, right? Let's say this is fwx, right? Is it correct? What's the problem of this notation? Let's think about one more case. Okay, let's say we have one more training data set, like this one. Let's say this is x10 and y10. It's going to be 100, 1, like this. If there's one more samples here, the regression function would be something like this one, right? What does it mean? What does it mean? By using this mapping function, we would like to well approximate the training data set. What does it mean? Okay, let's say we have a testing data set that whose size was here. Let's say x star is 12, right? Then if we use this one, the output of this sample is something like this one, right? But in case of this mapping function, the output is something like this, right? So in this case, it might be, okay, let's say y star is equal to 0.4, right? Something like this, right? But if you think about the training data set, this sample should be malignant, right? But as you can see here, if we just use the regression technique, we cannot find out the good prediction. So we need another approach to solve this problem. That's why we introduced the classification technique. Then, how can we solve this one? How can we solve this classification problem? Here's our strategy. So first of all, we can normalize the output of the mapping function. Let's say fwx, w transpose x. Okay, so let's say, okay, so something like this, right? First, we can normalize the output of the mapping function between 0 and 1, like this, and we can use the thresholding at 0.5 here, something like this technique, right? So in this case, we can say that if the tumor size is larger than this point, okay, let's say if the tumor size is larger than this point, it will be positive class or the one class. or if the tumor size is smaller than this point, it should be negative class, right? That's the strategy of the classification problem, classification technique. Okay, so in the more mathematical way, in the mathematical notation, we can write down this procedure, something like this. If the output of the mapping function is larger than or equal to 0.5, let's predict the y is equal to 1, and or if the output of the mapping function is smaller than the 0.5, let's predict the y is equal to 1. Y is equal to 0. So this is the strategy of the logistic regression problem. Logistic regression technique or classification technique. Okay, then how can you do that? Okay, let's see detail. First of all, we want the output of the mapping function is between the 0 and 1, right? To use the this thresholding, right? Then how can it constrain our output of the mapping function between 0 and 1? We need a nonlinear function. What is that? Okay, here is our nonlinear mapping function here. This nonlinear mapping function is defined 1/1 plus exponential negative z. So for example, let's say this is the z, and this axis means the gz. Then the shape of this mapping function looks like this one. This one. Okay, so what does it mean? Whole possible values can be z value here, but by using this mapping function, we can normalize this z to some predefined space 0 and 1. 0 and 1 here, right? So this is the new nonlinear mapping function. So by using this g of z, we can redefine the mapping function f w of x as a 1/1 plus exponential minus double transpose x. So in this case, this function is called the sigmoid function or logistic regression function. Okay, let's compare the mapping function in the regression problem and this classification problem. Okay, so if you remember the regression problem, the mapping function looks like that. Okay, f w x was w transpose x, right? We can draw this procedure as some dot product with the parameter and here, right? It was the mapping function in the regression problem, right? Then what is the mapping function in the classification problem? It's something like 1/exponential minus w transpose x, right? Then we can represent this procedure w and nonlinear term g and here, right? This is the main difference between the regression problem and classification problem. So in this case, this term, this nonlinear mapping function, is called the sigmoid function, right? Whose shape looks like this, right? So for example, if we draw this nonlinear term exactly, it looks like this. So here, for any x value, for any z value, we can map the any z value to the output value within the 0 and 1, like this. So this is the exact shape of this z function, or g function, right? So here, so here's our new strategy. Okay, so let's say if the output of the mapping function is larger than 0.5, this case in here, which is same as the W transpose X is larger than 0, this point, right? Then in this case, we can say that Y is equal to 1. Y is equal to 1. So again, so W transpose X is larger than 0 or equal to 0, and FWX is larger than 0.5 or is equal to 0.5, then we can predict what Y is equal to 1. Or W transpose X is smaller than the 0 and FWX is smaller than 0.5. In this case, this term, we can predict the Y is equal to 0. So in this case, W transpose X is larger than 0 and W transpose X is smaller than 0. Okay, so here's the new strategy of the classification problem. Okay, so is there any problem so far? Is there any problem? Oh, no. Is there any question? Okay, so if not, let's continue. Okay, so in here, we say that the output of this mapping function is the estimated probability that Y is equal to 1 on Xn, input Xn. So in other words, output of the mapping function is going to be the probability of the Y is equal to 1 given X, given input X here, and parameterized W, the model parameter W here. So this is a probability, right? And we already know that the probability that Y is equal to 0 and probability of the Y is equal to 1 should be, they are summed to the 1 value, right? Because they are probability, right? In other words, the probability of the Y is equal to 0 is going to be the 1 minus probability of the Y is equal to 1. So in other words, this can be something like this one, right? So this is the probabilistic explanation of this classification mapping function. So here's an example. Let's say the input X is going to be X0 and X1, and X1 is 1, and X0 is 1, and X0 is the tumor size. And let's say we already have the mapping function. It means that we already have the learned parameter W. Then output of this mapping function is the 0.7. Then in here we can say that tell patent that the 70% of the there is a 70% chance of the tumor being malignant, or there's a 30% chance of the tumor being non-malignant. So by using the mapping classification mapping function, we can understand the probability of the some happening. Okay. Here's one more concept: decision boundary. So the mapping function of the classification Fw of X looks like this, right? That the G was the was that? G was the sigmoid function. Sigmoid function, right? And let's say there is a two feature, x1 and x2. Then in this case, the learnable parameter have the three unknown variable, w0, w1, and w2, right? And we can rewrite this mapping function as this notation, right? The shape of this function looks like this one, right? And then here, this is the final mapping function, right? And the goal of the classification learning is to find out this mapping, this learnable parameter. How to compute compute the parameter w, right? For example, let's say w0, w1, and w2 is something like -2, 0, and 0. Then the shape of this term, looks like this. What does it mean? What does it mean? We already know W transpose X is larger than 0, then output should be 1, or W transpose X is smaller than 0, output should be 0, right? So in other words, if the W transpose X is larger than 0, in case here, the Y should be this part, right? Or if W transpose X is smaller than 0, the region should be subtractive, right? But as you can see here, this classification is not a good prediction. Why? Because there are some kinds of error here, right? Then the optimal classification rule should be something like this, right? Maybe if the W transpose X is larger than 0, the positive region lies in here, or the W transpose X is smaller than 0, the negative side should be defined here, right? So which is one of the best solution of this classification problem, right? In this case, the W0 is equal to -3, W1 is equal to 1, W2 is equal to 1. Define this mapping function. Define this straight line. Okay, let's say this is straight line. So in this case, this parameter W0, W1, and W2 might be the solution of this classification problem, right? Then in this case, this function is called the decision boundary. In other words, the goal of the classification problem is to estimate the decision boundary, define something like this. This is our goal. So, for example, in this case, the optimal solution was the W0 is equal to -3, W1 is 1, and W2 is equal to 1. Then this inequality represents this part, and this inequality represents this part, and W transpose X is equal to 1 decide the decision boundary. Decision boundary. Okay, so this is the definition of the decision boundary. In other words, the goal of the classification is problem is to estimate or to predict the decision boundary. Okay. Okay. So, is there any questions so far? Is there any question? No? Okay, so then let's continue. Okay, so far we will talk about the linear decision boundary. Linear decision boundary means only linear terms define this decision boundary. But how about this case? How about this case? In this case, if feature vector define the two feature x1 and x2, right? Then in this case, we want to classify these two samples, these two kinds of set of samples using the classification algorithm. How can you do that? Then another question is, what is the optimal decision boundary of this case? What is the optimal decision boundary? Maybe this one or this one, right? But as you can see here, it's not optimal, right? To classify this sample properly, the decision boundary, the optimal decision boundary should be defined something like this. Maybe this circle boundary, the circle shape of the decision boundary would be optimal, right? So in this case, decision boundary. So in this case, this circle shape would be optimal decision boundary, right? So then the question is, how can I find this nonlinear decision boundary? If you remember this one, we cannot find out the circle shape if we only considering the W0, W1, or W2, right? Then we need another terminology, right? Then here's the thing. Okay, so let's say Fw of x is going to be the G of W transpose x, right? Then in this case, we would like to define the higher dimensional feature. For example, the skew term. For example, this term is the nonlinear term. Nonlinear term, right? Then we can redefine our mapping function as this one, right? Right. Then, in other words, we can use this nonlinear mapping function to define our classification problem. Then, by using the sum method, we can find out this random parameter W1, W0, W1, W2, W3, W4, right? So in this case, W0 was the -1, and W1 is the 1, 0, and W2 was the 0, and W3 was 1, and W4 was also 1. Okay. Then the inequality of this classification problem is going to be something like this, right? In this case, this term is represent W transpose x, right? In this case, x is going to be W1, W2, W1 square, W square, right? And in here, if the -1 plus the W1 square plus W2 square is larger than or is equal to 0, then the output yn, we can predict the output yn is equal to 1. Or if this term is smaller than the 0, then output y1 up to yn is equal to 0. In other words, the decision boundary define W transpose times x equal to 0, right? So in this case, -1 plus x1 plus x2 square is equal to 0. It's going to be W1 x1 square x2 square is equal to 1. This is the decision boundary of this problem. Okay, so as you can see here, by using the nonlinear mapping function or the nonlinear projection, we can deal with the nonlinear decision boundary as well, or nonlinear classification problem as well. Okay, so this is the nonlinear decision boundary. Okay, so this is the classification problem. Is there any questions so far? We don't have any questions today, so you can ask. Yeah. In this case, G is also logistic function as well. Okay, so 네, 이 경우에는 x가, 그러니까 기존에는 우리가 x1, x2로만 정의 내렸던 거를 이제 사실 인풋 피처는 x1, x2 두 개긴 한데 이제 뭐 어그멘티드 피처라고 해서 x1의 스퀘어한 값이랑 x2의 스퀘어한 값을 모두 이용해서 x를 이제는 4디멘전의 벡터로 바꿔서 풀어야 되는 거죠. 이런 케이스에는. 네. Right. So the goal of the classification algorithm is to find out the decision boundary, and to define the decision boundary, we have to calculate the optimal weight W0, W1, W2, W3, right? Logistic yeah. In fact, in the regression problem, we can also deal with the nonlinear case if we can introduce the higher dimensional polynomial, something like this one. 제가 저번 시간에는 좀 넘어갔는데 사실 그러니까 리그레션 프로블럼도 우리가 이 매핑 펑션 텀을 그러니까 하이 오더 텀, 그러니까 논리니어 텀들을 정의를 내리면 사실 논리니어한 리그레션 프로블럼까지도 풀 수가 있어요. 이동적으로. 근데 저번 시간에 좀 우리가 설명을 쉽게 하려고 사실 리니어 텀만 설명을 했는데 네. 바로 익스텐션이 가능하고요. 네. 오케이. So okay, then let's continue. Okay, so let's summarize. We have a training set similar to the regression problem, right? The main difference here. This is a categorical variable, right? And one sample, or let's say n sample is defined as a xn is equal to the feature vector, like this one. In this case, large differs one-dimensional vector, and generally the x0 is equal to 1. Actually, this term is related to the bias, which will be the really important concept in the neural network or the deep learning. But in this case, let's say this is just a bias term. Anyway, which will be discussed later in our course, but in here, just keep in mind, this x0 is equal to 1 is for the bias term. Anyway, yn is equal to 0 or 1, and the mapping function of the classification problem was defined something like this, right?
please remember that the difference between regression mapping function and classification mapping function. Regression. Regression and this case logistic. Regression or classification problem.
Okay. Then similar to the regression problem, the question is how to find the optimal parameter W in here. This is our goal, right? And we can also use the optimization. Oh, sorry. Okay, let's continue. Okay, how can we solve this one? How can we find the optimal parameter W? We can use the similar optimization technique, such as the gradient descent. Okay, so first of all, we have to define the cost function first, right? In previous lecture, we introduced the two kinds of cost function, right? The first one is the mean square error. The second one is the mean absolute error, right? In here, we can use the simple cost function first. Let's say mean square error. Then, okay, let's define our cost function for the classification problem. So it looks something like this, right? In this case, xn is the input, right? Yn is output, and this one is the mapping function of the classification problem, right? How can we define this one? It was 1/1 plus exponential minus W transpose xn, right? Right. So if you remember the regression problem with the mean square error, what was the shape of this loss function? What was the shape of this loss function with respect to the W? It was like a ball here, right? Actually, in the optimization field, this shape is called the convex. 혹시 뭐 질문하셨나요? 아니면 넘어가겠습니다. 네, okay. So in regression plus MSA loss generate the cost curve looks like this one. In this case, FWX was the W transport T, right? It was a simple case. In this case, we can easily find out the optimal parameter by using the gradient descent, something like that. So we can start from here, then we can follow the path like this one. It was the gradient descent. But here's the problem. In classification algorithm, okay, let's say classification plus MSC, the mapping function FWX and it looks like this, right? Right? In this case, the loss curve with respect to the W looks like this. You can draw this one yourself, but if we draw the function with respect to the W here, it looks something like this. This is due to this nonlinear relationship. Nonlinear relationship. Okay, you know what I mean? What is it? Sorry.
nonlinear relationship. Okay. So in this case, if we start from here, it will be really challenging to align the global optimum term, right? So in this case, this is called the non-convex shape. So it's really hard to convert by using the MSE in classification problem. Here's the problem. So in other words, to solve the classification problem, we need to define another cost function to solve this problem. So here's the thing. So here's the cost function for the logistic regression. So our goal is that we want to make a convex cost function even for the logistic regression. In other words, okay, let's say our goal convex cost function with respect to W in classification problem. Okay. Here's our goal. So particularly, we have a very beautiful mathematic tools to define something like this one. So here's the thing. So the cost of the logistic regression can be separately defined for the yn is equal to 1 and yn is equal to 0. Okay, before defining, let's think about the desirable shape of the logistic regression problem. First of all, let's say yn is equal to 1, positive class, right? Then the output of the mapping function, our mapping function is equal to 1. And in this case, it means the correct prediction, right? In other words, y is equal to 1. It's our goal, but our prediction is also 1. So in this case, we predict well. We predict the training data. We explain the training data well, right? So in this case, the cost function, the output of the cost should be 0, right? Because this mapping function is the good, maybe optimal, right? However, ground truth yn is equal to 1, but our prediction, our output of the prediction is going to 0. In this case, it's not correct. It's not a optimal mapping function, right? So in this case, the cost of this mapping function should be what? Should be large enough. So it means that if the mapping function, the output of the mapping function is 0, right? But yn is equal to 1, we have to penalize the learning algorithm by very large cost, right? Then, which cost function satisfy this rule or satisfy this desirable property? Here's the thing. Okay, let's say here is okay. We already know the output of the mapping function is between 0 and 1, right? So we only need to define the mapping cost function within this here, right? First of all, when f is going to 0, the cost should be infinity, and fwxn is equal to 1. The cost should be 0, right? So we define this kind of loss function. What is that? First of all,
what is the shape of the negative log? It looks like no. Something like this one, right? Similarly, we can define the cost function when yn is equal to 1. It looks like that. So this term with respect to the fw of xn should be something like this. Something like this. So in this case, if f of x is going to be 1, the cost should be reduced or decreased. Or if f of x is going to 0, the cost should be increased. Something like this. So this is our new cost function for the logistic regression problem. So is there any questions so far? 이 부분은 중요하니까 한국말로 한 번만 더 설명을 할게요. 그래서 이제 우리가 앞에서 설명했던 것처럼 우리가 이제 클래시피케이션 문제를 풀기 위해서 이제 코스트 펑션을 정의를 내려야 되는데, 우리가 기존에 알고 있었던 민스퀘어 에러를 가지고 코스트 펑션을 정의를 내리려고 보니까 리그레션 프로블럼에서 코스트 펑션을 MSE를 썼을 때는 이렇게 쉐입이 이렇게 아름답게 나오는데, 이런 로지스틱 리그레션 매핑 펑션에서는 어떤 논리니한 텀들이 있으니까 해보다 보니까 이렇게 논컨벡스하게 나오는 거죠. 그러니까 우리가 이제 해야 되는 거는 우리가 원하고자 하는 디자이러블 프로퍼티는 가지면서 컨벡스하게 잘 나올 수 있는 매핑 펑션일 필요성이 가지게 되었고, 그래서 이제 이걸 위해서 이제 다음과 같은 코스트 펑션들을 정의를 내리게 됩니다. 근데 이제 이러한 경우는 뭔 얘기를 하냐면은, 그러니까yn이 1일 때, 그러니까 우리가 파지티브라고 에스티메이션 해야 될 때 우리가 매핑 펑션도 1에 가깝게 나와야 되는 거죠. 근데 반대로 이 아웃풋이yn이 1인데 우리 매핑 펑션이 0에 가깝게 나온다면은 코스트를 엄청 크게 줘서 그 러닝 알고리즘을 바꿔야 되는 거죠. 근데 이 두 개의 프로퍼티를 가장 잘 만족하는 이제 매핑 펑션 쉐입이 이제 다음과 같이 그려지는 거고요. 그래서 이제 이런 매핑 펑션을 가지고 우리가 로지스틱 리그레션 문제를 풀었을 때 우리가 원하고자 하는 컨벡스한 코스트 펑션을 가지면서 우리가 원하고자 하는 매핑 펑션의 아웃풋이 잘 에스티메이션 됨을 확인을 할 수가 있습니다. 이제 이러한 매핑 펑션, 이제 코스트 펑션 for logistic regression이라고 말할 수가 있습니다. fx is equal to 0. 이게 뭘 그러니까 우리의 매핑 펑션 아웃풋이 0에 가깝게 나올 경우를 말하는 거죠. 그러니까 우리가 fwxn이yn이 1인 경우에는 1에 가깝게 나와야 되는데 러닝 알고리즘이 잘못되었기 때문에, 즉 w가 잘못 찾아졌을 경우에는 제가 0으로 나오는 경우가 있잖아요. 그런 경우에 제가 1에 가깝게 나오도록 w를 바꿔야 되는 거죠. 근데 그게 우리가 러닝 알고리즘을 풀어야 되는 문제니까요. 네. 잠시만요. 어제까지 뭘 같지 않는 거 라지 미스테이크와 그렇다고 볼 수 있을 것 같아요. 네. 그러니까 사실 엄밀히 얘기하면 잠시만요. 그렇죠. 네. 그러니까 우리가 MSA랑 MA도 사실 엄밀히 얘기하면은 두 번째 프로퍼티를 만족하지 못했잖아요. 그러니까 그래서 이제 우리가 로버스트한 코스트 펑션들이 정의가 됐다고 했었고, 뭐 휴버놈이나 아니면 뭐 터키놈 같은 게 나왔다고 했는데, 여기서도 사실 이 코스트 펑션 자체는 이러한 두 번째 성질을 만족하지 못하는 게 맞고, 사실 이걸 위해서 또 다른 로버스트한 코스트 펑션들이 있지만 리그레션과 동일하게 이제 이렇게 정의 내린 로지스틱 리그레션을 위한 코스트 펑션, 그러니까 이 텀이 이제 로지스틱 코스트 펑션이라고도 하는데, 이 로지스틱 코스트 펑션을 썼을 때 어떤 이피션트, 그러니까 계산량에서 어떤 이피션시를 얻을 수 있기 때문에 사실 쓰는 게 제일 큰 이유인 것 같아요. 네, 맞아요. 그러니까 세컨드 프로퍼티는 사실 갖지 못하는 게 맞는 것 같습니다. 네. 그렇죠. 그러니까 이게 이제 제가 저 이제 이 슬라이드 마지막에 보면은 이제 이렇게 이쁘게 정의를 내리면 이거를 우리가 사실 제일 시간이 많이 들리는 거는 우리가 그레디언트 디센트에서 백프로파이션 학습해야 되는 거잖아요. 그레디언트를 계산을 해야 되는데 저기 익스포넨셜 텀이 있고 로그 텀이 있는데 쟤네들을 잘 그레디언트를 계산해 보면 정말 재밌게 나와요. 그러니까 정말로 간단한 품으로 정리가 되거든요. 그렇기 때문에 우리가 억지로 로그를 넣어서 억지로 넣은 거 아니고 많은 이제 수학자들 예전부터 어떻게 이러한 프로퍼티를 만족하는 펑션, 매핑 펑션을 코스트 펑션을 만들었을 때 이러한 특성도 가지면서 이피션시 측면에서 가장 효율적으로 풀 수 있을까라는 고민을 이런 로그 텀으로 정리를 한 거죠. 네. 사실 이러한 프로퍼티를 만족하기 위해서는 뭐 쉐입이 이래도 될 거고요. 그렇죠? 사실 뭐 이렇게 정의가 되어도 될 거예요. 그렇죠? 뭐 반대로 이렇게 정의가 되어도 돼요. 그렇죠? 그래도 사실 이것들을 다 만족을 하잖아요. 근데 이제 우리가 이렇게 로그를 써서 정리한 이유가 앞에 말씀드린 것처럼 이피션시가 제일 중요한 이슈이기 때문에 라고 보시면 될 것 같아요. 오케이? 네. 이거를 제가 슬라이드 보면서 한번 더 설명을 드릴게요. 이 부분도 한국말로 한번 더 설명을 드리겠습니다. 이 부분이. 자, 요거를 보면 되는데 우리가 가지고 있는 트레이닝 데이터셋은 그러니까 첫 번째 가정 그러니까 우리가 트레이닝 데이터셋에 가장 잘 맞는 매핑 펑션을 얻고 싶어 하지만 실제로 우리가 가지고 있는 트레이닝 셋은 완벽할 수가 없어요. 그렇죠? 그러니까 트레이닝 셋에는 아웃라이어도 있을 거고 노이즈도 있을 거고 왜냐면 트레이닝 셋 자체가 어떤 옵저베이션이기 때문인 거죠. 네, 일단 첫 번째 질문부터 설명하고 넘어갈게요. 그래서 무슨 얘기가 되냐면은 실제 트레이닝 샘플들이 막 이렇게 존재를 하지만 어떠한 샘플들은 이렇게 아웃라이어로 이렇게 존재를 할 거예요. 그렇죠? 왜냐하면 모든 샘플들이 다 완벽하게 릴라이어블하다고 가정할 수가 없기 때문인 거죠. 그렇죠? 이런 경우에는 사실 우리가 머신러닝을 왜 하느냐 그러니까 학습을 왜 하느냐를 생각해 보면은 테스팅 과정에서도 좋은 결과 그러니까 테스팅에서 들어온 샘플에 대해서도 좋은 에스티메이션을 내기 위함인 거죠. 그렇죠? 근데 그 관점에서는 우리가 매핑 펑션 이렇게 찾는 게 어떤 새로운 샘플이 들어왔을 때 좋은 정답을 만들어낼 확률이 높은데 이렇게 어떤 아웃라이어가 있을 때 매핑 펑션이 이렇게 변해버리면은 사실 우리가 원하는 답은 여기인데 이렇게 잘못된 답을 얻어내는 거죠. 그러니까 다시 얘기하면은 트레이닝 샘플 측면에서는 어떤 옵티멀한 로스가 사실 이렇게 찾아지는 게 더 로스 값은 작을 수는 있었지만 우리가 실제 테스팅 과정에서 좋은 결과를 내기 위해서는 사실 이렇게 찾았던 게 많았다는 거죠. 그러니까 이게 우리가 이제 다음 시간에 볼 어떤 뭐 오버피팅, 그 다음에 어떤 제너럴라이제이션 투 뭐 테스팅 데이터 뭐 이런 얘기들이 나올 건데, 그러니까 이론적으로 무조건 트레이닝 샘플에 잘 맞는 매핑 펑션이 사실 옵티멀은 아니다라는 거죠. 이 얘기를 이제 다음 시간에 다룰 건데 그 관점에서 우리가 어떤 러버스트 펑션을 써서 이런 아웃라이어를 다루지 않을 수 있다면 아웃라이어들을 지울 수 있다면 그래서 이런 펑션을 찾을 수가 있다면 우리가 어떤 제너럴라이전 파워에서 가장 좋은 매핑 펑션을 찾았다고 할 수가 있는 거죠. 이 부분에 대해서는 사실 다음 시간에 조금 러닝 티어리 파트에서 조금 더 자세하게 다뤄보도록 하겠습니다. 네. 그 두 번째 질문이 어떤 경우에 이 부분 말씀하시는 거죠? 이 부분? 그렇죠? 이런 거죠. 그러니까 우리가 원하고자 하는 거는 자, xn이랑 yn 둘 다 가지고 있어요. 그러니까 xn에 매핑되는yn을 알고 있죠. 우리는 트레이닝 셋에서. 그렇죠? 그 말은 뭐냐면 yn이 1이면은 우리가 원하는 거는 fwxn이 1이 나오길 바라는 거죠. 사실. w가 잘 학습이 됐다면. 근데 어떠한 이유로 그러니까 w가 잘못 학습이 돼서 fwxn이 0이 나와버렸다 라고 하는 거는 w가 어떠한 우리가 원하고자 하는 옵티멀이 아닐 확률이 매우 높기 때문에 그 w를 1에 가깝도록 바꿔줘야 되는 거죠. 그렇죠? 근데 그 w를 어떻게 바꾸냐? 이 코스트를 거의 무한에 가까운 코스트를 줌으로써 이 코스트를 낮게 만들도록 w가 업데이트가 될 거고 이제 그레디언트 디센트가 될 걸로 그러다 보면 이 fwxn이 1에 가까운 값이 나오겠죠. 네. 그게 이제 우리가 이 클래시피케이션 프로블럼에서 어떤 러닝 알고리즘을 통해서 업데이트하는 룰이라고 보시면 될 것 같습니다. 네. 됐나요? 네, is there any question from the foreigner student? Okay, then let's keep going. So this is a one case when the yn is equal to 1. And here's another case in yn is equal to 0, right? Then let's think about the desired property when yn is equal to 1. Similar to here, if
편하게 있습니다.
죄송합니다.
아주
If yn is equal to 1 and fwxn is equal to 0, this is a good estimation, right? So in this case, cost should be 0, right? But yn is equal to 0, but fwxn is going to be 1. The cost is going to be infinity, right? This is our desired property in classification problem, right? So similarly, the shape of this case should be something like this, right? Something like this. So in this case, when fwxn is going to 0, the cost should be 0. Cost is going to 0, right? In the opposite case, the cost should be maximized, right? So this is a cost function for the logistic regression problem when yn is equal to 0. Okay. To summarize, the cost function for the logistic regression is defined something like this. So this is the general rotation of the cost function. Here, the cost function for the logistic regression is defined to the two-way. When y is equal to 1, it should be something like this. And yn is equal to 0, it should be something like this, right? Oh, by the way, please think about the negative log 1 minus x. It's going to something like this, right? Please remember this one. Anyway, and here we already know yn always 0 or 1, right? Because this is the classification problem. You already know yn is equal to 0 or yn is equal to 1 always, right? It means that we can write this cost function in a single equation, something like this. Here, this cost function is going to be negative yn times the log fxn minus 1 minus yn times log 1 minus fwxn, right? So this is the single equation for this logistic regression problem. We can rewrite this one. For example, yn is equal to 1. This term will be 0, right? Then in this case, c is going to be minus log fwxn, right? Or yn is equal to 0. In this case, this term will be 0, right? Then in this case, this term is 0. So c is equal to negative log 1 minus fwxn, right? These two terms are exactly the same. Okay, so we define the cost function for logistic regression as well. Now we are ready to optimize the cost function classification problem. Okay, so similar to the regression problem, we can use some gradient descent algorithm to estimate the optimal parameter W. Let's talk about this one in Wednesday. Okay, thank you very much. So this is the end of today's lecture. Thank you. So if you have a question, please let me know or yeah.
그 질문은 아닌데
네.